We ended last Tuesday, looking at units of pressure. So we have all of these units, and at some point in your general chemistry career, you might be expected to do conversions between any of those units. As far as this class goes, you're really going to be responsible for knowing how to set up those conversion factors. So you'll be given information about what those conversions are. We don't expect you to have these memorized. Okay. The one that most everybody seems to remember, including myself, as far as our standard pressure unit, is atmospheres. Any idea why we remember atmospheres? Because our standard atmospheric pressure that we all kind of work in is just 1 atmosphere, so it's really easy to work with as far as a unit. Okay. The rest of them all have some root back into history or applications. Okay. So you're responsible for knowing how to convert them, but you don't need to memorize any of those. Okay. Questions on that? The ideal gas behavior. Okay. This is kind of a fun one because when we talk about ideal gases or mathematical manipulations, we have to make these assumptions. If we don't make these assumptions, our mathematics become massively more complicated. Okay? Gases are super, super tiny. So if we look at a balloon that has a bunch of gas particles in it, what we're referencing is that that balloon is holding its shape not because of the volume of each particle, but of the motion of that particle, effectively. Okay? So our gases, the molecules themselves, have no volume. Okay? So they do not contribute to the overall volume of your system. They move very rapidly. That's ultimately what's contributing to your volume, is their motion and thereby their pressure on their surrounding environment. Okay? And we also assume that they move in random directions and in straight lines. Okay? That just makes life a little bit easier when we think about how these molecules can interact with each other. Okay? When it gets into the attractive force between them, we assume that they do not attract one another, okay? Which could very well be untrue. If we have a positively charged gas particle, what might it be attracted to? A negatively charged gas particle. Can we have positive and negative particles? Yeah, absolutely. Okay? So what we're assuming when we move into that gas phase is we negate all of those potential interactions. Because if those interactions do show up, it again makes our mathematics a lot more complicated. One of the other assumptions is that when they collide, they lose no energy. Okay? This is referenced as an elastic condition, or elastic collision, as opposed to inelastic. So they hit and completely bounce with the exact same energy in changing directions, but the energy is still the same. And then our average kinetic energy is proportional to the temperature. Okay, that means if we increase the energy of the system, okay, we're increasing the temperature. Okay, if we increase the temperature, we expect the energy to go up. Okay, so it's just looking at a direct relationship between those. So where we ended on Tuesday was looking at potential variables that affect the gas pressure. Okay, and I'd kind of asked for you to think about it a little bit over the weekend. What things might affect pressure? Okay. So how is pressure affected by temperature? So if we came up with just a relationship, we've got our pressure and we've got temperature. How are they related? What's that? Don't get too specific into electrons, because when we're looking at gases, we've removed the complete concept of subatomic particles. We just have an atom. Okay? That atom, yes, is made up of protons and electrons, but we don't look at an electron interaction between atoms. So it's just the atoms.
The particles are spread out. The increase of temperature.
So what we're really pushing for is just basics. If we increase the temperature, what happens to the pressure? It increases. So if we increase pressure, we expect our temperature to go up. If we increase temperature, we expect pressure to go up. Okay? And vice versa. So if we're going to take that information and try and convert it into some kind of mathematical expression, Okay, that's where it becomes a little bit trickier. We can't say they're equal to each other because they aren't. Okay, there are other things that contribute to pressure. But we can look at a proportionality. So what we're saying by that, and there's a couple ways we can do this, is that pressure can sometimes use little squiggly lines, or you can use the proportionality symbol, is related to temperature how? Okay, well, if we increase pressure, temperature must go up. Okay, so we can use those squiggles to say that. And what that's meaning is that we are directly related. Okay, so if we increase the pressure, temperature increases as well. Okay, if we want to turn that into an equality, okay, so that they equal each other somehow, okay, what we're going to have to do is introduce some kind of constant. So we can say pressure is equal to our temperature times some constant. Okay, what symbol do you want to use for a constant? Okay. You can use a K. At this point, it doesn't matter. All we're saying is that if we just change pressure and temperature, they're going to be related through some constant. Okay, whatever that constant might be. So that can help us now come up with an expression to relate these two things, okay, which is what we're going to look at in a little bit. Is there something else that affects pressure? Elevation and gravity. How do I want to get in with that? I would put gravity as a form of pressure, so I wouldn't really call it a variable that affects pressure. And then elevation, yes, the pressure changes, but why does the pressure change?
Pressure affects pressure.
Okay, we could just say, yeah, then pressure directly affects your pressure. Okay, so that doesn't quite help.
Are we also looking at it like in the ideal?
Yeah, we'll assume everything in the ideal situation. I heard somebody mention volume. Okay, what's actually holding it in? So if we even looked at pressure with our atmospheric, our elevation changes. If we go to the center of the Earth, what happens to our pressure? It's really, really high. What's the volume of the center of the Earth versus the outside? We get a much smaller volume on the inside. Okay, so what we're looking at is a relationship to pressure. Sorry, pressure to volume. Okay, so we'll switch this up with our color. And we know that there's some relationship between those. Okay. It's a little bit hard to do with our Earth because we're looking at other contributing factors, and then when we get to the center of the Earth, we aren't really looking at a gas anymore. We're looking at solids and liquids and all of that. Okay? And that also does bring in this gravity contribution. So if we think just to a balloon and keep it as simple as we can with just a balloon, what happens when we shrink the volume on our balloon? So if you take a balloon, how would you shrink the volume? Okay, if you release the gas, you're changing another variable. You're changing the amount of gas that's present. Okay, so what we're trying to do is just keep pressure and volume, keep everything else constant. Okay. How do you shrink the volume of a balloon? Compress it. We take the balloon and we just push inwards. Okay, what happens to the pressure? It increases. Interesting. So what did I do to the volume when I compressed that balloon? Shrink it. So when the volume goes down, what happened to the pressure? It went up. Okay, if we go through the same kind of ideas we were doing before, okay, what happens now? How is pressure related to our volume? It's inversely related. So, how do you spell inverse? Always find some backdoor. Okay. If we just went through and said volume like this, what are we saying? With that mathematical expression, if I increase our volume number, what happens to the pressure? It would increase. Is that what we observe? No. So how do we mathematically fix that equation? Take the inverse of something. What do? 1 over that number. So if I take that volume now and I shrink that, okay, so let's say the volume initially started at 1. What would be our pressure? 1. 1 divided by 1 gives us our pressure of 1. What happens if I shrink that volume now down to 0.1? It's 1 divided by 0.1. Okay. Some of you may be able to do that in your head. If you can't, you can punch it into a calculator, and the number you get is 10. So when we shrunk the volume, what happened to the pressure? It increased. We now have a proper relationship based on our observable. Okay? And this is what was happening way back when they were looking at these gases. They effectively had a balloon and said, what happens when I start to change these variables on it, and see the relationships that pop out of it. Okay? If we now wanted to go through and set up an equality where we could solve it, okay, it turns out that if we go through and plot all our data, we get a very similar situation as we had between pressure and temperature. That I can then set these equal to each other and then multiply by a constant. Well, what constant are we going to use? Why should we use K? Wasn't K the constant between pressure and temperature? Okay, keeping your variable simple is one thing, but if your variable is related in a different situation, in theory it's going to be a different variable, a different constant. So what we might do is introduce it as a different letter. Throw in G. Doesn't really matter. Okay. Is there something else that contributes to our pressure? You actually already alluded to it a little bit earlier with our volume. So let's not change the volume, let's not change the temperature. But now I'm going to take that balloon and I'm going to hold the shape of that balloon, maintain it at a constant temperature, and I'm going to blow into the balloon. What have I changed? The amount of the gas, okay, which is technically also a mass as well. But which one do we typically use when we look at our calculation? Amounts or mass? First step with all of your conversions. Convert your mass into moles. What are moles? An amount. It's the number of them. So what we're looking at is a direct relationship between the pressure and our moles, okay, or our amount. Actually, I already gave that answer away, but let's go through and describe that. What happens, to our pressure if we increase the moles? Increases the pressure. Okay, and that then says we have, again, a direct relationship between our pressure and our moles. We could go back to our mathematical situation. We've got pressure is related to moles. Being the creative people we are and ultimately lazy, do we actually want to write out moles? Okay, every time you deal with a calculation, you want to write out moles each and every single time. How many of you have been using complete units in all of your conversions? That's what I thought. Okay. Chemists are just as lazy as you. We don't like writing out moles, okay? Particularly when we're looking at a mathematical equation, because in a mathematical equation, every single letter represents a variable. Okay? But when we move to chemistry, what happened with our balanced equations? Okay? A single letter could expand to represent a single thing. For instance, lithium we don't write out as just L. We reference lithium as Li. Okay, so we can use multi-letters to represent a single variable. So that could, in theory, be okay here. The issue is that this was, again, a very old subject, and instead of using moles, okay, where they didn't actually have a concept of moles, they just looked at the amount, they came up with a new symbol. Okay? An amount is ultimately referencing the number of that individual species. Okay? Or moles, an amount, or a number of those molecules. Any idea what symbol we use?
Smiley face.
Smiley face. Not a bad one. N. N represents our moles. And if we wanted to turn it into an equation, we'd go through and do the exact same thing we've been doing for everything else, N times some constant. So we've got these three equations, all related back to the same value, all back to pressure. So somebody was able to collect all of this data and looked at it and said, okay, you know, if I manipulate this in this way and this way, we could set up and condense these all into a single equation. That single equation, let's see, whoops, is all related out to a single constant. Okay, so all of those constants that we collected up on one term, okay, in each of those equations, we could collect and group all of those constants next to each other. Oops. And we end up coming up with this expression. Okay. And from this, we can actually see all of these individual relationships. Okay. For instance, okay, we said pressure and temperature. Okay, we're related how? Directly or indirectly? Directly. Okay, so let's rearrange this equation such that we can see that direct relationship. Pressure needs to be one side of the equation. Where does temperature need to be? The other side, so that we can see that relationship between them. So let's rearrange this equation. Okay, we'll get pressure on one side, and we want temperature on the other. So I'd have my constant. And how would temperature show up on the other side of the equation? Multiply both sides by T, and I can get temperature onto the other side of the equation. If I also decide to now go ahead and get the pressure and, or sorry, not the pressure, the moles and volume over to the other side, okay, you can get this kind of expression. And you look at that and you say, well, that's not the same expression that we had before when we looked at the relationship between pressure and temperature. We just said it was pressure is equal to our temperature times some constant. All right, well, this clearly isn't just a constant because I can change the volume and I can change the moles. But when we look at that relationship, do we change the moles? If we're looking at just the relationship of pressure to temperature, are we allowed to change the moles? Why not? It changes our entire expression. So when they look at the relationship, or when we think about the relationship between pressure and temperature, we don't change the moles. Well, if the moles never change, what can you tell me the moles are? Constant. What's a constant times a constant? A constant. Yes, that number has changed, but we haven't specified a number behind it, so it's just a new constant. If we look at that pressure to temperature relationship, could we change the volume? Was that allowed to happen? No, which means what happens to our volume? It never changes in the course of our test between pressure and temperature. Our volume is a constant. Well, what's a constant divided by a constant? Also a constant. And the relationship we get is pressure will be equal to our temperature times some unknown constant. How would we discover what that constant was? You'd have to run an experiment, okay, where you test pressure and temperature at multiple values and see the relationship between them. Plot that data and determine what that constant was. Okay? So what we did was take these kind of independent seeming systems or we've changed our pressure and our temperature, or we look at volume and pressure. And we define these individual relationships, and we come up with these new expressions that we just walked through. Okay? And then somebody looked at that very carefully and said, can I combine all of that information into a single expression? Okay? That single expression gives us the freedom to see each of those individual relationships. And as long as we keep variables constant, we can go through and determine what our answer would be, or the relationship between those pressures and temperatures. And that's ultimately what the gas law chapter is about. It goes through and discusses all of these individual relationships, and it takes you to this expression at the bottom. PV over NT equals a constant. Okay. Being, again, the lazy people we are, do we really want to write out constant every time we want to use it? Okay. Probably not. Okay. What symbol did we decide to use for that constant? Talked about a few of them. K. If you move into 152, you will learn to hate the symbol K because it's used as a rate constant and an equilibrium constant. Okay? Drastically different things, but the exact same variable. We don't want to bring that in here. Okay? We talk about K as well. It's also used, I think, as Boltzmann's constant. So K is used in too many different places. Okay? What's that? Temperature shows up as a ton of different variables as well, because we could use a lowercase t now to look at time, a capital T to look at temperature. So T is a busy constant, or a busy letter to use as our constant. Okay? What letter do we use to represent what this constant is? All of the alphabet is at our free disposal. Okay? Not only is it the entire English alphabet, we could also use the Greek or Latin alphabet. Okay? So we've got all sorts of possibilities. The constant that we all settled on, or that apparently none of you settled on, sorry, apparently your opinion was usurped, R. Okay? R because the letter R shows up multiple times in the word constant. Okay? It's also typically referred to as the gas constant. And gas in German happens to begin with the letter R. Don't quote me on that. Anybody know German? Oh, then I'm right. Okay. Until you can disprove me, I'm always right. Okay. So our gas constant is this letter R. What units might we expect for that gas constant? Okay, this becomes a trickier question.
Whole numbers.
Numbers aren't a unit, so that doesn't quite work. It's going to be the units based on whatever our units were for pressure, volume, N, and T. Well, what units do we use for N? Moles. Okay, pick the easy one first. What units do we use for T? We got degrees Celsius, we got Kelvin, we've got Fahrenheit. We've got all possible units that we could use for temperature, 3 different ones. Okay, what units are typically used when we're looking at our gas laws? Kelvin. Okay. Can we use degrees Celsius? Absolutely. That one's actually still a little bit tricky to deal with. Why might we use Kelvin instead of degrees Celsius or Fahrenheit?
Because it doesn't have negative.
It has to do with signs. Okay, temperature, if we look at our equation, can we have a negative pressure? Don't get overly sciencey on me. Can we have a negative volume? Can we have a negative amount of atoms? No. So the only term in here that can be negative is temperature. Okay, so if you only bring in one negative, what does that mean? Something else would have to be negative, and that gets really problematic when it comes to calculations. Okay, so the temperature unit we use is going to be Kelvin, because Kelvin can't be negative. Can't. Okay, what's that? Oh, it's a B.
That's like
Shucks.
gasoline.
Then it's Latin. The Latin word for gas begins with R. Stop checking me. I'm glad that didn't get recorded. Pressure and volume. What unit do we use for volume? Volume?
Liters.
We could use cubic centimeters. Okay, but centimeters are typically a measurement of length or distance. So we tended to convert our cubic centimeters into a different unit. What was that different unit?
Liters.
Liters or milliliters. When we work in the lab, what volume do we typically work with? Milliliters. Okay, why? We can't use too much. So when we're looking at liquids and solids, we use milliliters because it's a relatively easy value to manipulate. If we put you up at liters of liquids and solids, that's a lot of volume. Okay, but if we're going to work with a gas, does it make sense to work with milliliters or liters? Why liters? If we look at the volume of a gas in a milliliter, or even the amount of gas particles in 1 milliliter, we get a very, very small amount. Very difficult to work with that amount. So if we want to see a reaction that allows us to see a large change in units, we'll typically use liters. Okay, so our units for volume kind of stand out nicely as well. We're up to liters. So we've come up with nice explanations for 3 of our units. Now pressure. What units do we use for pressure?
Inch pounds.
Inch pounds is a possibility. Okay. PSI is a possibility. Torr is a possibility. Millimeters mercury is a possibility. The conversion between all of those is a multiplier. Okay. So it is very easy to switch between those units. Okay. So depending on what you're trying to do, that unit drastically changes. Okay. Or depending on who trains you on what unit to use. And when it comes to chemistry, we just talked about what unit we preferred for chemistry. ATM, or our atmospheres. Because when we're working with standard gases, okay, in just a normal environment, our pressure is right around 1 atmosphere. Okay, it's an easy number to work with. Whereas if we move to millimeters mercury, was it 760 millimeters mercury? That's a big number. We'd have to multiply that. That's way too much work. Okay, so we focus on this atmosphere unit. So when we're looking at our most commonly, these are the units you'll work with. Atmospheres, liters, moles, and Kelvin. Can you switch outside of that realm? Absolutely. Right? If you moved into any other chemistry class, you will be asked to switch out of that realm and deal with those other units. Right? But ultimately all it is just another conversion. You just have to be aware of what units you're using for your gas constant. All right, which brings up the next idea. That may be our units, but what number does our gas constant come out to be? How would we figure that out? Can we measure a pressure? Particularly in atmospheres? Yeah, we can use millimeters mercury. We can use all of those methods to determine a pressure. So I can determine the pressure of an individual system relatively quickly and easily. Can I determine the volume? Is it possible to determine a volume of an object? Yeah, so we can get the value, the number for our volume. Can we determine the temperature experimentally? Yeah. Can we determine the gas? The amount of gas particles? It's a little bit trickier, but we can determine that as well. So if I can get numbers for each of those for an individual system, what can I do? I can put all the numbers in and solve for what the gas constant comes out to be. Okay? That was done a long, long time ago. They keep refining the number. But what we end up finding out is if we use these units, that gas constant is 0.0821 atmospheres times liters per mole Kelvin. Okay? So if you want to determine what the pressure is within an individual system, what do you need to know? Okay, I give you a problem and I want to know what PA is. What is the pressure in some unknown system, A? How would you solve for it? What do you need to know? Is there an equation that relates pressure to anything else? Kind of sitting right in the middle there. I see a PA, right? Do I have an equation that relates PA to anything? That's a yes. If I want to solve for just the pressure, okay, what we could go through and do is use our algebra. Don't plug in any numbers, but use the algebra to get PA all by itself. Okay, what would it equal?
PA equals.
So I got an R. It's a good place to start. PA equals R. What else? Times the moles in that system times the temperature in that system divided by the volume of that system. Okay? What we've done here is actually a conversion. We're converting the units of pressure, the units of moles and temperature and volume into the units of pressure through our gas constant. This expression becomes ridiculously famous and comes out in certain variations of it. Most people seem to remember this part, okay? Where the pressure is equal to, usually written out as N RT over our volume. Okay? Or as my high school chemist attempted to do in the DMV and then got a ticket, rearranged her license plate to be PV NRT and then got some electrical tape, put that onto her onto her license plate. She has the equation PV equals nRT. We now have the ideal gas law. Right? This gives us that R, gas constant. It allows us to convert between pressure, volume, moles, and temperature. Right? Most commonly, or at least how I was always taught to pronounce this, anybody know how to pronounce that? PIVNERT. Okay, if you know PIVNERT, you can now do any gas law equation because they all come back to this expression. Okay. Everybody's going to say it with me. PIVNERT. I didn't hear you. Say it again. I didn't hear you. Let's get some excitement into this. Come on. I still see mouths not moving. Do it again. A little bit more. A little bit more. Come on now. Okay, I guess that's enough torture. That expression is all you need out of the gas chapter. PIVNERT. Every question thrown at you comes back to that equation. And what you end up doing is simplifying things. So if we're told what happens to the temperature, what's the temperature of a system, if it's pressure, let's clear all that away. What's the temperature? Okay, if our pressure is changed from 1 atm to 2 atms, if it started at, if our temp started at, let's say 298 Kelvin, can we solve for that new temperature? Good question. Volume and number of moles. According to what we just talked about, all we need is PIVNERT. Okay, but in PIVNERT we have volume and moles. Do we need the volume and moles to solve this equation? No. Why not? Because they're constant. They stay constant. Okay? So what we're saying is that if we take R and we take our pressure at our conditions 1, our volume at conditions 1, our moles at condition 1, and our temperature at condition 1, we know that if we look at our R constant for the pressure at conditions 2, volume at conditions 2, moles at condition 2, and temperature at condition 2. Well, what's the R at condition 2 versus the R at condition 1? They're the same, which means I can now say P1 V1 over N1 T1. But what did we say was the difference between our moles and our volume? What happened to them in the course of this question? Nothing. So V1 equals V2. N1 equals N2. So what happens to those terms? They cancel out of the equation. And I end up with a new expression. What's that new expression? Careful, there's an equal sign there. P2 over T2 equals P1 over T1. Okay. Do I know what my pressure was? Changed from 1 atmosphere to 2 atmospheres. Plug the numbers in. Do I know what the temperature was? I know the conditions, 298. Temperature was 298. For which one? P1 or T1? Why do you know it's P1? Does it really matter? No, as long as you're consistent. If we say 298 is P2, what's the pressure at P2? 2 atmospheres. This expression is completely generic, and as long as you order your temperatures and pressures with the same constant or the same variable, you'll always get the correct answer. Okay? So you have to go through and take this equation or that word expression and say that at 1 atmospheres, I'm looking at P1, which means at 298 Kelvin, what am I looking at? T1. What was 2 atmospheres? What was 2 atmospheres? P2.
Are you sure it's not the other way around?
Yeah.
It says it changed from 1 to 2, but it started at 298.
So if it starts at 298 and our pressure went from 1 atmosphere to 2 atmospheres, where did we start? 1 atmosphere or 2 atmospheres? Started at 1 atmospheres and it was increased to 2 atmospheres. So your initial temperature is T1. Yes. Is it tricky? Yeah. Make sure you read your questions carefully to make sure you assign what those variables were. Right? And then ultimately it's just plug and chug into that R expression. Okay? And they may not tell you that your volume remained constant. To solve this question, did the volume have to remain constant? The way the question's phrased, it absolutely does. You must make that assumption. If you don't make that assumption, you cannot solve the problem. Okay? So ultimately what we can get is now any rearrangement. So if you're given of those 4 possible variables, pressure, volume, moles, and temperature, if you're given any 3, you can solve for the 4th. If you're given a system where the conditions change around you, you can also solve for it. Okay? So we end up with that fun little expression, Pivner. We can solve for multiple different conditions, either gas at conditions A or conditions B, which is what we just walked through. Okay? So let's take a look at an actual expression. Okay? This one's a little bit trickier. The volume of a container is doubled. Assume the temperature and the moles are not changed. So this time we actually told you that. What happens to the pressure? Okay, why do you say the pressure drops? So if we think back to our expressions, what's the relationship between pressure and volume? Inversely related. So if I double the volume, that means this number gets what? The volume gets bigger, which means what happens to the pressure? It gets lower. What you just did was a quick approximation that could now eliminate probably 2 answers on a multiple choice test by knowing the relationship between those. How much did it exactly change by? What's that? There are numbers. This is why I gave you this one, because this one doesn't give you specific numbers, but I want you to manipulate the equations and see what you can come up with as far as determining what exactly happened to the pressure. Okay? So, we work through it on your own, or you want to start piecing things together, doing some conversion stuff first?
Together.
Okay, we'll work on it together. The volume of a container is doubled. Mathematically, what does that mean? Okay, times 2. So if we look at our initial volume, okay, it's some unknown term. Okay, I don't know what that number is. Okay, but I know it's some volume initial. So we can put some question mark. I don't know what it is. But what's my volume final? Question mark times 2. A question mark's kind of obnoxious to use. What could we use instead?
V1.
How about V1? 2 times, or I've been using VI, but it's fine, either way. Okay. Assume our temperature and moles are not changed. What does that mean? N initial equals N final. Oops, not volume. Temperature. Temperature initial equals temperature final. What happens to the pressure? So what we're now asking for, with all of that information, is we have a pressure initial equals something that we don't know, and our pressure final equals something that we don't know. What we want to know is what happened to that pressure final. Okay? So what can we go through and do? We've got 2 conditions. If you've got 2 conditions, what's the gas constant for those 2 conditions? There's a hint. The gas constant. It's the exact same, which means if I set up an expression, P initial times V initial over N initial times T initial, what does that have to equal? P final, V final, over N final, T final. I can't solve that equation directly, but do I have some information I can plug into it? So V final is 2 times V initial. So we can do that substitution. What else do I have? I have the moles and the temperature. What have I been substituting in? Initials. So let's get rid of these guys. I know my N final equals N initial. My T final equals T initial. What can I do now? What am I trying to solve for? Which pressure am I trying to solve for? The final pressure. All right? So we can now rearrange our equation. I'm going to have to erase all of our given information now. P final equals what? P initial. I want to be a little bit. So P final's over here. So let's first Does this need to change at all? No. So let's just copy that out. V1, or V initial, N initial, T initial. These red terms now need to be what? Where do they need to go? Should they be left next to P final? No. So where do they need to go? The other side of the equation. How do I get them to the other side of the equation? Multiply and divide. How do I get 2V1 or V initial to the other side of the equation? I will divide by 2 times V initial. Everybody see that? What mathematical operations are we using? Everybody's favorite. Algebra. This is straight algebra. Okay? What makes this even trickier is that what we're asking you to do is use variables, not numbers, because numbers are completely meaningless if you don't know how to plug them in. What happens to the T initial? Where does that need to go? That needs to be shuttled to the top of our expression. What happens to the N initial? Shuffled to the top. Can we simplify that expression? What's T initial divided by T initial? 1. But you don't know the number. How can you possibly cancel that out if you don't know the number? It doesn't matter. 200 divided by 200 is 1,000 divided by 1,000. You don't need to know the number. You need to understand how to manipulate the variables. What's N initial divided by N initial? What's V initial divided by V initial? What am I left with? P initial over 2. What happens to my pressure? It's cut in half. In our initial assumption, Brian had said that our volume needs to decrease. If our volume is cut in half, did it decrease? Yep, there it is. Okay. The expressions can solve it for you as long as you go through and use your algebra. Trust the algebra. Do not trust the numbers. Okay. What happened if we doubled the temperature? It's a trickier one. What happens to the pressure? We double the temperature but keep everything else constant. Pressure needs to increase. Why does the pressure increase? Remember our expression. Pressure is directly related to our temperature. The pressure ends up doubling. Okay? We could go through, I lost connectivity. We can go through and follow the exact same math, the exact same algebra, and solve, and we'll notice that we get the exact same, almost the exact same result. That if we double the temperature, because pressure and temperature are directly related, what's going to happen to our pressure? It must also double. Okay? It's going back to just Pivnert. Play with Pivnert, manipulate those equations around, and everything solves out for you. Okay? The one caveat, in this situation, we don't worry about units. Okay? In a lot of the situations that you may encounter in the future, what will you encounter? Units. So what do you need to make sure happens when you go through and you do all this algebra? That the units cancel. If the units don't cancel, you can't do the direct conversion. Okay, so you may have to convert your units into the appropriate format so that your units do cancel out of this. Is there a question there?
Kind of. Instead of using the P over NT model, I guess never mind. I'm have to because of the initial and final.
Yeah. And this expression gets you to that same idea. Okay, you get the same result. Why? Where did this expression end up getting put into? It's the exact same thing. Okay? So as long as we keep everything constant except for those two variables, we can use that expression. right? Because the constants will cancel out. So here, how many moles of neon gas occupy 2.34 liters at STP? Standard temperature and pressure. Standard temperature is 273 Kelvin. Standard pressure is 1 atmosphere. Kind of an obnoxious question because there's multiple ways to solve it. What is volume? Divided by, what is R? Not quite. 0.0821. Liters times atmospheres per mole times Kelvin times what? 273 Kelvin. What do you do? Track your units. Kelvins cancel. What happens with atmospheres? Cancel. Liters cancel. So we get 1 divided by 1 over moles, which is also equal to moles. So our units check out. So now we can plug it into the calculator. And the answer we get, did anybody actually solve it this way? What do you get for a number? 0.105? So what you guys got to? Close enough. Is there another way to solve this problem? Yeah, there is. But arguably, this is the easier way to solve it. Okay, because you all said Pivnert like 60 times, so now Pivnert is stuck in your head. You're tired of listening to me say Pivnert. Let's try it again. What does it say? Pivnert. There we go. Exciting. R. R is a gas constant. Where are constants typically provided?
On the test.
On the test. All you have to remember is Pivnert. That's it. You can solve and get the answer. Was there another way to solve it? Yeah. Is there a relationship? Whoops. What were we given? 2.34 liters to moles.
2.4.
What did you say? 22. Oh, okay, 22, yeah. Yeah, if you remember last week, we said it was 22.4 liters is 1 mole. So why don't you just memorize 22.4 liters is 1 mole? Because it's not always 22.4 liters. So you're not just memorizing 22.4 liters is equaling to what 1 mole, because that number is not going to be given to you on an exam. What else do you have to memorize? That equation is only valid at STP. You may not be told STP. You may be told at 273 Kelvin and 1 atmosphere, or 760 millimeters mercury. Right? If you don't have all of that information memorized, you've now invalidated the use of this equation, and if we tweak one subtle change off of our temperature or pressure, your calculation is wrong. However, if you use what I'm telling you to use, which was Pivnert, you'll never get it wrong. Okay? Because this equation is always true, not just at STP, at all temperatures, at all pressures. There is nothing else to memorize except Pivnert, because the gas constant undoubtedly is given to you, unless your instructor is really mean, in which case I apologize. I'm sorry for you. Okay? But almost always that gas constant is supplied for you. All you need to know is Pivnert. No numbers, no units, no special conditions. It's a lot easier to manipulate all of your gas rules through that simple equation Pivnert. Okay? Even something that you go, oh, that's a simple conversion. It's only a simple conversion because you know what the conversion is. If you don't know what the conversion is, you're screwed. So use the equation.
Grams.
If I gave you grams, okay, you'd have to string together a bunch of other conversions. And it does make things more confusing. Pivnert will always work. Unless it's not an ideal gas, but it will be. Okay? Try another one. That's a lie. What's wrong with that question? I mean, you could potentially solve for it, but it's going to be a little bit weird. Are you going to be able to get a number at the end of this? You don't have a volume. Without the volume, you can't solve for it. Okay, so you'd figure out the relationship between moles and volume. What would that relationship be? 1 mole is, it'll end up coming out to 22.4 liters. So we would have that relationship solve out of this if we really wanted it. Okay. Last thing we'll talk about, I hope, with gases, because I find them kind of boring. Law of partial pressures. Okay. What we're saying with this is that since, remember, in our ideal gas situation, none of the particles have any attractive forces for each other, and all particles, regardless of what elements are contained within that particle, occupy the exact same space, which is nothing. Which means if I'm going to look at the pressure for an individual system that has a mixture of gases, the total pressure will be equal to the pressure of each of the individual species. Which is kind of a neat approximation. Okay, but if we compared hydrogen gas to iodine gas, it's probably not a perfect comparison. Why not? What's the difference between hydrogen and iodine? Where's hydrogen on the periodic table? The very first element. How big is hydrogen? It's the smallest element we have. Where's iodine? The lower right-hand corner, pushing towards the largest element we have. Okay? So in that system, we would probably start to deviate away from this exact relationship. Okay? But in most circumstances, we approximate the sum of each of the individual pressures of each of the individual gases will equal our total pressure. If we look at the gas of any one of those, or the pressure of any one of those individual species, that is referred to as the partial pressure. So you end up with this neat little expression. So if we take a look at this equation, good, I kept the units all the same. The sample of noble gases contains helium, neon, argon, and krypton. The partial pressure is all of those numbers. What is the total pressure of the sample? All you got to do is add them up. What if I didn't give you the millimeters of mercury? Okay, so another theoretical solve. You always love these. The millimeters of mercury for argon. I don't tell you that. Can you solve for the pressure of the argon? If I tell you the total pressure. So if I now tell you your total pressure is, pick a number that I think will work. Yeah. Let's do 400 millimeters mercury is the total pressure. Can you solve for the partial pressure? What do? Okay, you subtract all of the individual pressures out of it. Okay? What you're doing in this case is the same thing you did with Pivnert. It's just algebra. Right? And if you rearrange that equation and then plug in the numbers, it can become a little bit easier. Okay? Questions about your partial pressures? Good. Oh man, more pressure stuff. The Kelvin scale is kind of based on temperature. Or sorry, based on our Pivnert expression, our ideal gas expression. And what they ended up discovering is that if we look at that relationship, we can actually extrapolate back down to the absolute smallest Kelvin value we can get. And that is our absolute zero, okay, which is negative 273 degrees Celsius. Okay? At absolute zero, theoretically, all things stop moving. Why do they have to stop moving? There's no pressure. Can an electron exert pressure? If it's moving and it has some mass, yeah. Be a very small pressure, but it can exert that pressure. So theoretically, if we hit absolute zero, what happens to even the motion of electrons? Stops. Okay, everything should cease to exist. Okay, so at 0 degrees Kelvin, we can't get to. Okay, interestingly enough, this is kind of a fun one. Physicists within the last, I think, 10 years were actually able to get negative Kelvin. Okay, based on some fancy manipulations of other thermodynamic valuables or variables. Okay, but for all intents and purposes, as far as we're concerned, absolute zero is the absolute lowest we can get, and we can't quite get there, but we can get darn close. Okay. There's the term known as entropy. Anybody heard of entropy? What is entropy a measure of? Disorder. Okay? So if you look at your room, what happens to your room that you're in? Does everything stay nice and perfectly ordered at all times? No, eventually it gets messy. Why? Your room is an example of entropy. Okay? Entropy always increases as far as our natural systems go. The only way entropy can decrease is if we put energy in to force it to go back to an ordered state. So what they were able to do with their experiment is they could prove negative temperatures, and at negative temperatures, things naturally transgressed or became ordered. Mathematically, completely nonsensical. Or actually, mathematically, it's sensical. Reality-wise, completely nonsensical. But they were able to get particles to go from a random state to a very ordered state at these negative temperatures. Kind of bizarre. Kinetic theory of gases. Why do gases fill our entire volume that contains them? Okay. Our gases are trying to get away from each other as much as possible, so they're going to spread out and equalize that area around them, which means they will entirely fill that volume until there's no interactions between them. Right? What happens to the amount of motion to the gas when the temperature is changed? It increases. So we're just looking at our particles moving faster when we heat things up. Okay? And what happens to the speed of an individual atom when we increase the temperature? It will also speed up. So the more interesting stuff, forces and implications into water and physical properties. So we'll go through kind of a simple overview stuff first. This is one of the first things I talk about in organic chemistry. Okay? Chemistry is, in general, the idea of any two atoms interacting with each other at its most basic level. And then we scale up to larger and larger systems. So what makes up the atom? Protons, neutrons, and electrons. So we could actually scale it down even further for chemistry, and chemistry is the study of any two things interacting with each other, where those things could be subatomic particles. When subatomic particles interact, what happens? They create atoms. Okay, once we have atoms, then what happens? Atoms can now interact with each other and become compounds. Okay, but then what happens when we've got compounds? Compounds can interact with other compounds, and we become new compounds. So chemistry is pretty much the scale all the way up from the subatomic particle all the way up to how larger molecules and systems work. And ultimately, all of the interactions that we see, okay, say between you and your pencil, okay, or you and your desk when you're falling asleep in class, okay, all of those interactions are ultimately coming back to chemistry, and we're looking at the scale of those interactions. If it's a really strong interaction, we might say they're covalently linked, which is why when you're walking down the hallway, your hand doesn't just fall off. Okay? Or when you put your head down on your desk, it doesn't fuse to the desk. But what happens if we increase the interactions on the desk? Say put down some glue. Now when you put your head down on the desk, the glue increases the interactions between your head and the desk, and now your head's stuck to the desk. Okay? I've never done that to a student, just so you know. It's my story, I'm sticking to it. So all chemistry is how do these things interact with each other? Okay? So when we look at a molecule, even when we scale up to that molecule, it's still really just two atoms interacting with each other. But it's what happened in each of those atoms. What causes that atom to be different than what it would be in just a normal situation? Right? So we get slight scales and variations off of these things. Those slight variations allow us to take an atom that would react violently in one condition, but when we change the atom or its interaction with other molecules, what happens? It can now become completely benign. For instance, sodium metal. Right? Not a particularly good thing to have around, right? Sodium metal, we throw it into water, what happens? Explodes, big violent reaction. It's one of our active metals. And yet, for your muscles to function, what do you need to have? Sodium. Go on. Then I should eat bricks of sodium metal, because then I'd be better at moving my muscles. Okay, then we would explode. So what's the difference? What has changed about the sodium? We've changed the electrons around it, which changes its ultimate interaction with everything else that it sees. Okay? And it goes from being ridiculously reactive to something that's relatively benign, and we can use that charge characteristics to allow our muscles to function. Okay? So very subtle changes in the overall atomic structure can make a massive change in the overall macro scale structure. So you guys saw these, where I looked at the interactions just between, we could say, smiley faces. Okay? And we get this general change in those reactions. And we could look at each of those stages as different levels of interaction. Right? When we move into the chemistry world, we're doing the same thing. We're looking at those levels of interactions and trying to name them or come up with ways to interact with them. Okay? Where we had started a while back was we broke that down into our different types of bonds. We could have ionic and covalent and polar covalent. And I'm definitely out of time, so I'm going to stop talking, sort of. Okay, so you can feel free to pack. We'll come back to this slide. You guys should remember, right? What is an ionic bond? What is a polar covalent bond? What is a covalent bond? Because once we know those, we can start to predict how our molecules will interact with each other in larger environments.